Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on nonlinear control systems. Today we are going to go through lecture number 5 of this course. So we start the lecture from the previous concept that where we finished lecture number 4, that is Groundwall Bellman inequality. So Groundwall-Bellman inequality is basically a relationship that converts an implicit bound on a continuous function into an explicit bound on the same continuous function. Implicit bounds are usually very difficult to deal with, and if y of t, the bound on y of t is depending upon the function itself, then it is very difficult to characterize or do some calculations that are meaningful using this bound. So Bellman Groundwall inequality basically converts such bound into this kind of a bound where the upper bound on the continuous function does not depend upon the function itself. Therefore we can do meaningful calculations using this bound. So why is this important? I've already told you that this turns implicit bound on y of t into an explicit bound on y of t. And why is it relevant to nonlinear control systems theory? Well, the reason is that if you look at the solution of the differential equation y dot equal mu of t y of t, so this looks like a linear equation, so a linear system. And the differential equation, and this, if you remember the solution of the linear ordinary differential equation, it's very similar to that, except that here there are x dot equal ax and plus bu, something like that, and the solution is x of t equal e to the power at times x naught plus integral of bu tau d tau and so on. So this is basically why this Groundwall Bellman inequality is relevant to the control systems theory, because of its similarity to the solution of a differential equation. All right. So that's all we are going to talk about Groundwall-Bellman inequality. Next, let's discuss the continuity of the solution of differential equation with respect to initial conditions. So consider a differential equation, nonlinear differential equation x dot equal f of t comma x of t, where f of t, x of t is a function of time as well as this function of state. It's a nonlinear function, and the initial condition could be anywhere in the n-dimensional Euclidean space. So we define a function psi, which is a function from the n-dimensional space onto the continuous functions with infinity norm defined on those continuous functions. So at this point we already know that this is a complete space. So a complete space is a space where every Cauchy sequence is converging. So this function, the definition of this function is that psi of x naught comma t is equal to x of t. So this is a function of the solution of this differential equation. So where xt is the solution of the differential equation with initial condition x naught. So we already know that psi would be continuous at x naught if for all epsilon greater than 0 there exists delta greater than 0, such that if the distance between x naught and z naught is less than delta, then this implies that the distance between psi of x naught and psi of z naught is less than epsilon. So this is the standard definition of continuity of functions. We already have seen that. Or we can say that the supremum over all time, the distance between the two trajectories corresponding to two different initial conditions is less than epsilon. So if you look closely on this definition, where The closeness of the initial condition implies the closeness of the trajectories. So that is why we say this is continuity of the trajectory with respect to initial condition. This is very important and useful concept to know or to have in your knowledge, because if you want to if you can somehow characterize the upper bound on the distance or difference between the two trajectories given the upper bound on the difference between the initial conditions, that can be used for many different purposes. For example, the navigation, state estimation, or even when you're solving the interception type problems, or vehicle following problems, where you don't want the following vehicle to be, the trajectory to be much far away from the leading vehicle and so on. So continuous dependence on initial condition, there is a theorem regarding that. Consider x dot equal f of t comma x of t on Rn, and suppose that f of t comma x of t satisfies the condition of global existence and uniqueness theorem. Suppose that x of t and z of t are two solutions of the same differential equation with two different initial conditions, x naught and z naught. Then for all epsilon greater than 0, there exists delta greater than 0, such that if the initial conditions are within certain distance from each other, then the maximum or supremum of the distance between the trajectories would be bounded by another number which would depend upon this number. So I can also give you the dependence between the two numbers. This is the dependence between the two numbers. So if you keep the initial conditions within delta distance, if you want to keep the trajectories within epsilon distance from each other, then the corresponding delta can be calculated by epsilon divided by e raised to the power Lipschitz constant of this function. So remember that this f of x has to satisfy the global existence conditions, which means that it has to be globally Lipschitz. If it is globally Lipschitz, it will have some global Lipschitz constant L sub t, and then this capital T is the time up to which you want to keep the distance in control. So for example, you want the trajectories to be not far away, not farther than 5 units of distance from each other, and until the time of 10 seconds. Then capital T will be 10 seconds, T naught will be your initial time, maybe 0 seconds, and then this will be Lipschitz constant. You can take the Lipschitz constant times the difference between the two time values, the exponent of that, and divide by the bound of the difference between the trajectories. That will give you the required distance, the required upper bound on the distance between the initial conditions. So it's a very interesting tool to have in your bag of tools for nonlinear control systems analysis. So this is the delta that would work for each epsilon, and L sub t is the Lipschitz constant for the function f. So solution of the Lipschitz differential. So another thing that we can infer from this continuous dependence upon initial condition is that the solutions of the Lipschitz differential equations converge or diverge no faster than the exponential rate. So this is basically this exponential rate, basically this gives us that conclusion or remark that the distance between if there is a certain difference between initial conditions, then the initial condition times some exponential rate would be the difference, would be the maximum possible difference between the trajectories. So that's about the dependence upon initial. Next we look at the Lyapunov stability theory. So this is the analysis part of the course. So stability analysis, how do we analyze or define stability for nonlinear systems? So we would be looking at first we would be looking at time invariant systems because they are easy to understand, and then we can extend our concepts of stability to time varying systems. The learning of concepts through time invariant systems and then extended the concepts to time varying systems, that's probably in my opinion is the easiest way to learn the concepts of stability. Well, so define first of all, before we talk about stability, we have to define something called equilibrium point. So xe is an equilibrium point of a nonlinear differential equation if f of xe is equal to 0. That means that it is the value of x at which all the derivatives are equal to 0. So, or in other words, equilibrium point is a point at which the dynamics are 0. You can also call this f of x to be dynamics of x, and you can also call the equilibrium point as a point at which, if you start if the initial condition of this differential equation is xe, then the solution of this differential equation will be x of t for all time will be equal to xe. So the solution will be just a constant value. So this is the equilibrium point. It is also called critical point or static point, but in control systems theory we just call it equilibrium point. An equilibrium point is isolated. So this is the definition of an equilibrium point, whether being isolated or not isolated. So in linear systems there cannot be an isolated equilibrium point, but in nonlinear systems can have an isolated equilibrium point. And the definition of isolated equilibrium point is that if there exists alpha greater than 0 such that xe is the only equilibrium point in the ball of radius alpha around xe, then xe is the isolated equilibrium point. Suppose that xe is an equilibrium point of this differential equation x dot equal f of x, then we can do a change of coordinates to move xe to the origin. So this is an important remark because I'm going to use this remark through this implication is going to be used in the rest of the course. For example, let's suppose that this x dot equal f of x has an equilibrium point xe which is not 0. So this is a non-zero equilibrium point, and we want to make it a zero equilibrium point. So we want to shift the equilibrium point from non-zero value to 0 value. So how do we do that? We do that by shifting of coordinates. So you define new coordinates or new state vector x bar, which is the original state vector minus xe. Then what happens? Since xe is a constant, if you take derivatives on both sides of this equation, dx bar by dt will be dx by dt minus dx of e by dt, which is 0 because this is constant. xe is constant, it's a single value of x. So dx by dt, we already know that it is equal to f of x because x dot is equal to f of x, and so x is equal to x bar plus xe. So that would be like, instead of so x bar dot will be x dot, but wherever you have x in the function f of x, you replace x with x bar plus xe. So then for this new system, x bar dot equal f of x bar, because xe is constant, so we can call it f of it's just a function of x bar plus the constant value does not it's f is still a function of one variable. Here also f is a function of one variable, but this variable has this constant shift with it. So if whenever x bar is 0, f of xe, we already know that f of xe is 0. So now the equilibrium point of x bar dot is equal to f of x bar plus xe has been shifted to x bar equal to 0. So now in this course, all of the stability analysis is for equilibrium point at the origin, but the analysis is valid for all equilibrium points that are not at the origin. So, why? Because we can always shift the equilibrium point without any change in the differential equation. So remember that when we shift the equilibrium point from non-zero value to zero value, the differential equation remains the same. I mean the f function remains the same. So if the differential equation or the f function remains the same, that means that the properties of x bar dot equal f of x bar will be the same as the properties of x dot equal f of x. So stability property will be same. So that means that we can always assume that equilibrium point is at 0, and that would be valid for all other systems for which equilibrium point is not at 0. Next we look at the definitions of the stability. Let xe be an equilibrium point of x dot equal f of x such that there exists a rho constant rho greater than 0 for which the initial condition within the ball of radius rho around the equilibrium point implies that the trajectory will exist for all time and it is unique. So there is local existence, but the time is like in global sense. Again, we have an equilibrium point and we have a differential equation, and in the neighborhood of the equilibrium point, if the initial condition is in the neighborhood of the equilibrium point, then the solution will exist for all time. If that condition is satisfied, then we can define the stability xe. The equilibrium point is defined to be stable in the sense of Lyapunov if for all epsilon greater than 0 there exists delta greater than 0, such that if the distance between the equilibrium point and the initial condition is less than delta, then the distance between the trajectory and the equilibrium point is less than epsilon. So for all time t greater than equal to t naught. So this is the requirement of stability. If this requirement is not met, then the equilibrium point will be categorized as unstable. Similarly, if the equilibrium point xe is stable in the sense of Lyapunov and there exists some neighborhood eta of the equilibrium point such that if you start within eta distance of the equilibrium point, then your trajectory not only stays close but actually it converges to the equilibrium point. So if the trajectory is attracted towards the equilibrium point or converges to the equilibrium point whenever you start within eta distance from the equilibrium point, then that is sort of like attractivity. So stability plus attractivity, that is called asymptotic stability. And asymptotic stability is a stronger form of stability. So stability in the sense of Lyapunov, that only requires that if you start close enough to the equilibrium point, then you stay close enough. But asymptotic stability requires that not only you satisfy these conditions, but in addition there is some neighborhood of equilibrium point such that if you start within that neighborhood, then you actually converge to the equilibrium point. Here another remark is worth mentioning, that for linear systems attractivity implies asymptotic stability, whereas for nonlinear systems they can have attractivity without the stability. That would be clarified towards the end of this course when we will be studying limit cycles and other things like that. So that's the definition of stability and asymptotic stability in the sense of lab. Next we look at some demonstration of the stability concept. So the concept of stability in the sense of Lyapunov is that if this is a one-dimensional system and it's the trajectory, if you start, this is the equilibrium point value. If you start within the delta neighborhood of the equilibrium point, then you are guaranteed to stay within some epsilon neighborhood of the equilibrium point. Okay, this is the demonstration of stability. And asymptotic stability implies that in addition, if you start within, this is required for asymptotic stability as well, but in addition to this, it is also required that there is some non-zero neighborhood eta around the equilibrium point, such that if you start within eta neighborhood, then you eventually asymptotically converge to the equilibrium point value. So this is the demonstration of stability and asymptotic stability. That's the end of the lecture, and let's do a quick revision of what we have discussed today. So we have looked at Groundwall Bellman inequality that we already looked at in the previous lecture. It converts an explicit bound into it converts an implicit bound into an explicit bound. Then we looked at the relevance of Groundwall Bellman inequality, that it's very similar to the solution of differential equation. And then we looked at the continuity with respect to initial conditions of the solution of differential equation. So that was one of the concepts that we discussed in this lecture, that if two initial conditions are bounded by some value delta, then the difference between the trajectory will be bounded by some other value epsilon. And we also characterize the relationship between the delta and the epsilon in terms of the Lipschitz constant. And since this relationship has the exponential proportionality factor, so this distance between the trajectory is proportional to the distance between the initial condition, and the constant of proportionality is this exponential term. So that leads us to the conclusion that the solutions of the differential equation converge or diverge no faster than the exponential. No faster than the exponential rate means that the exponential rate is the upper bound on the expansion or contraction of the expansion or contraction speed of the differential equation. Lyapunov stability, we defined the equilibrium point. It is the point at which the dynamics are zero, and if you start at the equilibrium point, then you stay at the equilibrium point. And then we defined the isolated equilibrium point, the equilibrium point which has at least some non-zero neighborhood in which it is the only equilibrium point. And suppose that we also discussed the shifting of coordinates to convert the equilibrium point from non-zero value to zero value. The purpose of this discussion was that to justify that discussion of stability by assuming zero equilibrium point is enough for those cases as well where the equilibrium point is actually not at zero, because the stability property does not change by shifting the coordinates. And then we defined the stability in the sense of Lyapunov by epsilon delta definition. And then we defined the asymptotic stability, which is stability plus attractivity. And then there is a remark that linear systems cannot have attractivity without stability, but nonlinear systems can have attractivity without stability. Then we looked at the graphical demonstration of the stability definition and the asymptotic stability definition. Well, thank you for listening, and stay tuned for the next lecture.